Hello there and welcome back. Tonight we will drift ever so gently into a realm of calm exploration as we embark on a journey through time and innovation, discovering the engineering wonders that reside within the world of modern equipment. Fall asleep with the engineering wonders behind modern equipment, or, if it soothes you even more, let us softly echo fall asleep with how equipment transformed our world. A gentle journey, for these facts about equipment reveal more than nuts and bolts. They reveal a tapestry of human endeavor that has shaped societies, industries, and the very way we go about everyday life. Imagine, if you will, a peaceful workshop bathed in the soft glow of warm ambient light, where diverse tools and components sit quietly waiting to tell their stories. This workshop, like a silent companion, hums with a gentle energy, not the loud clamoring of heavy machinery, but rather the serene anticipation of creation and innovation. In the dim corners of this workshop, we can trace how simple machines evolved, precisely honed to tackle tasks that once consumed vast amounts of human labor, gradually transforming into the refined, efficient, and sometimes automated equipment we know today. As we step quietly into this world, notice the subtle shapes of metal surfaces glinting in the low light, each contour telling us of the care that went into its design. These items embody progression, from the earliest mechanical devices of ancient times, like levers and pulleys, to the much more complex wonders we see in agriculture, construction, and manufacturing. Let us begin with the historical backdrop of how equipment became such an integral force in shaping civilization. For much of human history, tasks like farming, building, and crafting demanded significant human effort. Early civilizations learned to harness the basic principles of mechanics. The lever, which multiplied force through its pivot, revolutionized our ability to lift objects that exceeded raw muscle power. Wheels and axles allowed large stones or heavy products to be transported reliably, bringing entire communities closer to one another. These basic tools, though simple in appearance, laid the foundation for increasingly advanced inventions. Over centuries, humanity refined these concepts further. The Greeks and Romans introduced sophisticated cranes and lifting devices, employing pulleys and counterweights that enabled the construction of awe-inspiring architectural feats. Through these small yet significant leaps, we see how ingenuity slowly transitioned into the realm of more complex equipment. Imagine gazing across a vast field of grain in times when people relied on handheld scythes and labor-intensive approaches to harvest crops. That ancient image stands in stark contrast to the sleek combine harvesters of today. But how did we progress from the humble scythe to the majestic harvester that can gather, thresh, and clean grains in one efficient sweep? The answer invokes centuries of trial and error, as inventors and blacksmiths experimented with new ways to enhance productivity. Simple hand tools gave way to horse-drawn plows, harrows, and reapers that cut manual labor in half. When the Industrial Revolution dawned, steam power entered the scene, further reducing the physical burden on farmers. Over time, steam yield gave way to internal combustion engines. Gradually, in the 20th century, tractors and harvesters became fixtures in agriculture, using diesel or gasoline engines to power robust mechanical systems that worked faster and more consistently than any horse-drawn apparatus could dream of. Today we witness the continuation of that lineage in sophisticated equipment brimming with sensors, GPS technology, and sometimes even self-driving capabilities, all quietly orchestrating an agricultural tapestry that feeds millions with remarkable efficiency. As we turn from the fields to the city skyline, we find a parallel story in construction equipment. Picture towering cranes, excavators with massive hydraulic arms, and bulldozers pushing mounds of earth without breaking a sweat. Each was born from the same fundamental mechanical roots but refined through an ever-expanding understanding of force, leverage and power. Steam-powered excavators once roamed construction sites of the 19th century, their steel arms hissing and puffing with each scoop. Over time, as demands for greater capacity and precision grew, the equipment scaled up. Combustion engines brought mobility and autonomy that trains and stationary steam machines could never match. With the rise of hydraulic systems, an astonishingly powerful technology harnessing incompressible fluid in cylinders, excavators, loaders, and cranes gained smooth, precise control over movements that previously required entire teams of workers employing ropes and levers. In these devices, pressurized fluid flows through carefully arranged channels, amplifying grip strength and reach. This synergy of power sources, fluid mechanics and structural engineering is the hallmark of modern construction equipment. Step closer and observe the wide stance of an earth-moving machine, anchored by robust tracks designed to distribute weight across soft or uneven surfaces. Notice the carefully placed counterweights that balance massive loads, preventing a crane from tipping over. Let your mind wander into the gearboxes and transmissions that convert raw engine torque into precisely tuned motion. Feel how each gear tooth interlocks to transfer force, ensuring that the right power is applied at the right moment. Far away from the hustle and bustle of a busy construction site, the same principles reappear in machines that shape the manufacturing world, weaving entire industries together behind closed factory doors. Think about the smooth automation of assembly lines. In these spaces, robotic arms lift, rotate, and position components with accuracy that can border on perfection. While it may seem effortless, the behind-the-scenes complexity involves a careful balance of material science, structural design, programming, and mechanical knowledge. The arms pivot with the help of electric motors, powered by meticulously balanced gear trains that reduce or increase torque to achieve the ideal speed and strength for each task. Many of these separate automated tasks run under the watchful eyes of sensors that measure distances, detect object positions, and ensure that every piece aligns flawlessly. Such precision becomes particularly crucial in fields like automotive assembly, where hundreds of parts must be married together into a single working vehicle. Even more subtle is the way manufacturing equipment manages heat, vibration, and wear, three invisible yet ever-present factors that can compromise longevity and performance. Engineers meticulously select materials that will withstand repetitive stress and extreme working conditions, ensuring that motors, bearings, and other moving parts harmonize for hours on end without any significant drop in efficiency. This engineering dance ensures that our daily essentials, from electronic devices to simple household goods, roll off production lines with consistent quality. Now, as you settle deeper into a calming state, let us take a closer look at the fundamental mechanisms that make all of this possible. Mechanisms that sometimes hide beneath protective casings or inside the hearts of these powerful machines. Hydraulics, for instance, are an ingenious method of transferring force. Within a sealed system of hoses, pumps, and cylinders, a fluid typically consisting of oil is pressurized by a pump, converting mechanical energy from the engine into hydraulic energy. This pressurized fluid then moves into cylinders with pistons inside, translating the hydraulic energy back into mechanical work. In an excavator, for example, each pivoting segment of the arm relies on a dedicated cylinder. Extending or retracting the piston rod allows the arm to lift or lower massive loads with astonishing grace. The advantage of hydraulics lies in how effectively they multiply force. By designing cylinders with different diameters, engineers can modulate how much lifting force is applied, granting machines the versatility to move both large and finely detailed objects. Gears, on the other hand, are an equally critical piece of the puzzle. On the surface, a gear system might look like a circle with teeth, but hidden beneath that facade is a carefully engineered ratio that defines how speed and torque will be distributed. A large gear turning a smaller one can increase speed at the cost of torque, while a smaller gear turning a larger one does the opposite, giving a machine more pulling force and less speed. Everywhere you look in modern equipment, from the largest earth movers to the quiet spinning mechanisms of a small workshop tool, gears handle and modify motion with elegant simplicity. Paired with gearboxes and transmissions, they direct the power output of engines or motors so that heavy loads can be moved without stressing the machine. Powering these mechanical wonders are engines and motors that have undergone centuries of refinement. The internal combustion engine once ruled as the beating heart of everything from farm tractors to construction vehicles. Spark ignition gas engines and compression ignition diesel engines each have their strengths. Gasoline engines can rev higher for lighter applications, while diesel engines stand firm in the face of immense torque demands. Over time, new materials like cast iron steel, aluminum alloy, and even advanced composites have been integrated, optimizing engines for endurance, power output, and efficiency. Now, as the world transitions toward more sustainable forms of energy, we increasingly see electric motors stepping into roles formerly dominated by combustion. These motors, relying on electromagnetic principles, convert electric current to mechanical rotation by spinning a rotor inside a stator. Electric forklifts, for instance, maneuver around warehouses with remarkable ease and minimal noise, their battery packs supporting hours of operation. In the near future, expanded battery capacity and greener production methods may pave the way for electric or hybrid versions of many types of heavy and industrial machines. Similarly, alternative fuels such as hydrogen or sustainably produced biofuels could further revolutionize how we power our equipment, granting us cleaner, quieter operations without compromising capabilities. But the transformation goes beyond just swapping engines. Equipment design also incorporates advanced electronics, from precision sensors that ensure tasks are completed to the exact millimeter, to onboard computers that allow real-time monitoring of engine health, fuel consumption, and potential inefficiencies. In agriculture, the concept of precision farming has made it possible to fine-tune exactly where seeds are planted, how much water is distributed, and where fertilizer is most needed, optimizing yields while reducing waste. This intelligent approach dovetails with our society's growing imperative towards sustainability. It also reveals the subtle harmony between long-standing mechanical concepts like torque, traction, and force distribution, and cutting-edge software that interprets data and guides the equipment's every move. When you pause to reflect on the artistry of equipment design, it becomes apparent that there is a delicate balance between form and function. Even in large, bulky machines, every contour, angle, and joint addresses a specific requirement. For instance, the shape of a bulldozer blade is carefully calculated to scoop and push earth efficiently. Meanwhile, the counterweight of a crane extends behind the tower at just the correct distance and mass to offset heavy loads. The geometry of gear teeth in a transmission is shaped to maximize contact area without overly increasing friction or heat. Material choices come into play too, as engineers weigh factors such as tensile strength, heat tolerance, corrosion resistance, and of course cost. Metallurgy has advanced considerably, with modern steels and alloys designed to meet exact performance demands. In some applications, certain components might be crafted from titanium for its strength and low weight. Other times, carbon fiber composites have quietly taken hold because of their high strength-to-weight ratio. Even in agricultural equipment, rust-resistant metals and coatings ensure that machinery can survive the elements season after season. This is the wonderful dance of engineering. Each part of a piece of equipment must complement the others, so that the final product merges endurance, precision, and safety into one cohesive whole. Let us wander next into the interplay of safety and efficiency. When you look at a piece of industrial machinery, perhaps a forklift or an aerial lift, you may notice safety cages, harness points, or load limit markers. These elements reflect not only functional attributes, but also regulations and best practices painstakingly formulated over decades. As industry matured, so did the demands for equipment that not only performed tasks quickly but also protected workers' well-being. Laboratories test everything from rollover protection to how well controls respond to operator input under stress. At the same time, design innovations reduce the burden on operators. Ergonomics, once an afterthought, now earns prime consideration, meaning that cabins, seats, control panels, and even the arrangement of pedals are carefully planned to reduce fatigue and discomfort. The broad arc of equipment evolution reflects our growing respect for the health and safety of operators. Where once a worker might have had to strain with a lever or spin a giant wheel by hand, now hydraulic joysticks, power steering, and adjustable seats reduce the risk of injury and help keep everything running smoothly. This synergy of mechanical ease, electronic feedback, and regulatory framework promotes a sustainable, safe environment for workers around the globe. With each passing year, new technologies emerge that whisper of more changes to come. Consider the rise of robotics and automated guided vehicles, which traverse factory floors along pre-programmed paths, delivering parts or materials without human intervention. Or the surge in 3D printing technology, in which components can be precisely crafted layer by layer, opening a world of complex shapes that used to be nearly impossible to achieve through traditional machining. Some production lines now integrate collaborative robots, so-called cobots, that work alongside humans, adjusting their force and movement based on real-time sensor input to avoid collisions. The future of equipment may be one where many tasks require only monitoring by human operators, aided by artificial intelligence that can adjust settings on the fly to maximize efficiency and reduce downtime. At the same time, even with all these remarkable shifts, there remains room for simpler equipment designed for smaller projects, personal use, or more localized industries. Hand tools and mechanical implements have never really vanished. Instead, they are refined to serve niches that massive machinery either cannot or should not enter. In smaller workshops, you might still see belt-driven lathes or milling machines that respond to the practiced touch of a craftsperson. These small-scale solutions embody the same principles used by larger machines but foster a closer harmony between operator and equipment. Meanwhile, in our ongoing quest for environmental harmony, designers increasingly look to reduce waste, limit emissions, and optimize resource usage. This might mean integrating solar panels on remote equipment that powers electronics, or using regenerative braking systems on electric construction vehicles that capture energy once lost as heat. It also includes exploring biodegradable hydraulic fluids or lubricants that pose less threat to surrounding soil and waterways. A gentle wave of eco-consciousness now permeates equipment engineering, driving us toward a cleaner, quieter, and more sustainable future. Let us reflect on the path that brought us here. From human muscle and animal power through steam-driven contraptions, from internal combustion to finely tuned electric motors, from manual levers and gears to computerized controls, the equipment shaping our world today is the culmination of countless experiments, failures, triumphs, and refinements. Even the shape of excavator buckets or the pitch of a fan blade might be the result of years of iterative testing, revealing that at the heart of modern equipment is an unshakable commitment to both practicality and improvement. It is a testament to human resilience and creativity that we have come so far in effectively multiplying the efforts of our own hands. As we consider specific examples, the smooth synergy between a tractor and its powered attachments reveals how mechanical couplings and power takeoff systems convert rotational energy from the tractor's engine into the torque required to run implements like balers, mowers, or seed drills. In construction, an excavator might swap its bucket for a hydraulic hammer, demonstrating that the same hydraulic connections can power different tools seamlessly. Back in the workshop, a lathe will spin a metal rod with perfect consistency, while adjustable cutting tools shave away material, demonstrating the principles of rotation, friction, and shearing. These same rotational forces appear in pumps that move fluids, fans that ventilate spaces, and turbines that harness or deliver energy. Everywhere we look, the language of equipment whispers the beauty of mathematics and physics tamed for human ends. Sometimes the seeds of new breakthroughs lie in combining existing technologies in novel ways. For instance, adopting the remote control logic used in drones might lead to teleoperated excavators, letting operators work from a safe distance in hazardous environments. Or we might see the precision equipment used in medical device manufacturing trickle into the realm of everyday applications, ensuring that assembly lines can handle even more delicate components. The overarching chord is that evolution in equipment often arises from convergence, a coming together of ideas, be they from different industrial spheres, academic research, or practical on-site problem solving. Another aspect worthy of reflection is maintenance, that often overlooked but vital dimension of equipment longevity. From greasing gears to ensuring engine fluids remain uncontaminated, from aligning belts to periodically inspecting the structural integrity of booms and arms, the care we invest ensures that these mechanical companions continue to serve reliably. Planned maintenance schedules, real-time diagnostic software, and predictive analytics can alert operators when bearings show signs of excessive wear, or when a hydraulic system's pressure has strayed outside normal bounds. This reduces the risk of costly breakdowns and extends the working life of each machine. A neglected machine, no matter how well constructed, gradually succumbs to friction and fatigue, but one that is properly maintained can remain in service for decades or even generations, forging a link between the past and the future. As you rest here, lulled by the gentle hum of imaginative workshop machinery, consider that in all these developments, we see the best of human potential harnessed toward progress. Equipment, once merely a way to save time, now embodies a harmony of mechanics, electronics, and creative problem solving. Engineers and designers around the globe,
devote themselves to making each component more durable, more energy efficient, and more adaptable to different tasks. In the background, entire fields like fluid dynamics, thermodynamics, control theory and material science converge on each new design. The result is a quiet revolution, one that does not always clamor for attention but steadily shapes industries, infrastructure and our common future. Every so often, you might find yourself drawn to the gentle silver curve of a gear, or the faint cabin light of a crane perched at the edge of a construction site, and in that moment you can remember the centuries of knowledge, trial and collaboration that came together just to guide that motion. Now, as the conversation unfolds into the night, let us unwind further by pondering the collaborative interplay of humans and equipment. That interplay defines not only how tasks get done but also how we evolve as a society. In the earliest times, labor was intense, requiring entire communities to band together for monumental tasks like harvesting, milling or building shelter. But with the advent of advanced tools and machinery, productivity soared. Freed from the physical demands of these tasks, we can invest brain power in creative pursuits, research and innovation. Yet we have also learned to remain aware of the responsibilities inherent in large-scale mechanization, recognizing the environmental impact, the ethical considerations of automating jobs, and the necessity of maintaining a skillful, trained workforce who can oversee, repair and operate these tools. Even as we integrate more automated systems, humans remain an integral part of the loop, ensuring that intellect and compassion guide how we adopt new technologies. That synergy is most evident in the modern fields of industrial automation, where the intangible intelligence of programming meets tangible mechanical frames. Code, written by human hands, instructs machines precisely how to move, when to clamp or release, and how to respond to unexpected deviations. This bridging between the digital and physical has broadened what we can achieve, from mass-producing vehicles to performing delicate assembly of electronics. Meanwhile, small startups can harness the same principles of robotics and instrumentation to produce specialized or custom products, effectively leveling the playing field in a global marketplace. And so, in large part, equipment is not just about doing more but about doing better, harnessing our resources efficiently, minimizing downtime and producing goods that reflect informed design. In the gentle hush of this moment, you might imagine the swirl of metal chips in a fabrication shop as a sculptor or machinist shapes raw material into something purposeful. Sparks may fly, but behind them lies a meditative dance of machine tools carefully removing or melding layers of material, creating precisely measured results that meet a design specification or blueprint. That measured approach is deeply rooted in science, from understanding tensile strengths to precisely calibrating cutting speeds and feed rates. Even the color temperatures of lights in production areas are sometimes chosen to reduce operator fatigue or enhance clarity. All these minute details, the spacing of rivets, the sequence of assembly steps, the distribution of torque on bolts, reflect an invisible web of knowledge that hunts for perfection in each piece of equipment and each process it supports. Perhaps the most breathtaking notion is the idea that even at rest, equipment is a testament to potential energy. A dormant crane stands tall, offering a silent promise that at the turn of a key and the press of a lever, it can lift immense loads toward the sky. A parked tractor suggests that, with a little diesel, it could venture across acres of farmland, tending the land sustainably and efficiently. A lathe, motionless yet quietly humming with possibility, can craft intricate shapes from a nondescript metal rod. These silent promises calm us with the knowledge that humanity's partnership with machinery can be fulfilling, guided by mindful engineering, careful usage, and a constant push toward improvement. In the coming years, we might witness unprecedented leaps sparked by emerging technologies. Quantum computing, for instance, might refine our ability to model forces, friction and materials at the molecular level, leading to equipment designs that stretch the boundaries of current engineering knowledge. Microsensors embedded in structural components might detect early signs of stress or wear before they become hazards, prompting preventive measures and extending service life. Meanwhile, manufacturing processes might evolve to minimize waste by recapturing fumes and scraps, turning them into new raw material for the next production cycle, embodying a cradle-to-cradle philosophy. And while large industrial complexes will continue to produce the heavy-duty machinery that reshapes landscapes, smaller workshops and local makers equipped with advanced tools may bring about artisanal production on demand. Yet as advanced as things might become, the time-honored properties of physics, geometry and material strength remain the common thread linking old and new. Each generation stands on the shoulders of the last, so that an engineer designing a new excavator bucket might combine centuries of trial and error knowledge with modern computational tools, bridging tradition and modernity in one fluid stroke. Reflecting on these quieter marvels, we see that there is a graceful dance in how equipment shapes our modern landscape. It builds roads that connect our lives, farms that feed our families, and factories that produce our daily essentials. In each of these achievements, the heartbeat of machinery is heard, though sometimes faintly, like a distant lullaby that underlies the progress of society. And though we may not always consider how a crane's boom or a combine's reel is designed, that design is integral in allowing the crane to lift a heavy beam precisely, or the combine to gather delicate crops without damage. If we reflect on the synergy between man and machine, we find a robust partnership, an evolution that started long ago and continues unabated. For you in the stillness of this moment, let the knowledge of such quiet, methodical advancements soothe your thoughts. Each nut, bolt, gear and beam is a silent testament to the power of gradual and cooperative progress, shaped by countless hands and minds over many generations. Now as you let your eyelids grow heavier, allow the mesmerizing equilibrium of hydraulics, the rotation of gears, and the hum of motors to guide you to a peaceful restorative rest. The path of equipment engineering is far from complete. New materials and cleaner energy sources will continue to reshape our machines, while software and data analysis render them ever more precise and efficient. But as you drift away this evening, know that these mighty creations are a testament to collaboration and determination, quietly bending raw forces to serve constructive purposes. Thank you for allowing me to share this calming exploration of the engineering marvels that build and sustain our world. May you carry a sense of awe for how equipment continues to evolve, gently revolutionizing the tasks we once thought were insurmountable. May it fill you with comfort to recognize that behind every lever, motor and circuit lies the story of humanity's best attempts to craft solutions that better our common life. So let those gentle mechanical murmurs guide you toward a serene and well-deserved slumber, and as you drift off, secure in the knowledge that tomorrow brings new frontiers of design and discovery, I wish you a restful night's sleep. Good night.